So let's begin differential equations. So first, the definition: a differential equation basically is an equation that involves one or more derivatives of the unknown function. Okay, so typically this unknown function is basically y of x, and the derivatives basically are represented, the dy by dx are generally represented as y dash, and d square, the second derivative, is represented as y double dash. So let me give an example. So say something like this: y dash whole square plus 2y dash minus 4 is equal to 0. So this is a differential equation where it has differential equation where it has the y dash terms, the y double dash terms, so the first order derivative term, and then the second order derivative term of the unknown function, which is y of x. So it might be y of t also. So typically x is the independent variable here, and the function, which is y, is called the dependent variable. So basically an equation, so so differential equation is an equation where you have the derivatives, one or more derivatives of the dependent variable, which is y. And so the objective in solving differential equation is basically to finding the unknown function y of x. F of x or y of x, whatever you want to write. Okay, so that is the main objective in solving differential equation. You have to find out this unknown function y of x. Okay, so why we need to solve differential equation? Or why we need to solve, or why we need to study differential equation? So this is the question which I'll be stating the reason. So if you go through all the physical laws and the relationship that exists between the quantities studied in various scientific disciplines, so it might be mechanical or it might be electrical, so all your basic physics equations, they are expressed mathematically as differential equations. So all your physical laws and the relationship between quantities, basically the physical quantities, studied in various disciplines, so these are expressed mathematically in the form of, so various scientific disciplines are expressed mathematically as differential equations. So for example, I'll give a beautiful example. How many of you are familiar with the Newton's laws? So if you recall Newton's second law, which is basically F is equal to ma. But how do you express? So if say I know the position of the particle, this represents the position of x of t, represents the position of the particle in time t, and m is the mass of the particle. So if a force f of t, so m is constant, so if a force f of t is applied on a particle, so what does Newton's law say? So if a force f of t is applied on a particle of mass m, then its position at t is related to f of t by the equation f of t is equal to m d square x by dt, where x is basically a function of time. So this is nothing but your acceleration term, the second order derivative of the position is basically the acceleration. So point here is Newton's second law, which is a basic starting equation for engineering mechanics. So in that, I mean, so the point we are making is most of the physical laws, and the example here, which is Newton's second law, it is expressed mathematically in the form of differential equation. So for example, Newton's law, you have the force acting on a particle is related to the position of a particle in this way. Okay, similarly, I can give you another example. If you have a biomass, say of a biomass m of t of a bacterial culture, so say some amount of bacteria, and that you are calling as a biomass. Okay, and that is, so the way it grows, the way the bacteria grows, that can be expressed in this form. So what it means is that the biomass m of t at any time t for bacterial culture growing in a uniformly supporting medium. So if you have some amount of bacteria which is growing in a favorable condition, you have favorable conditions or a supporting medium to grow, then the rate at which this mass increases, or the rate at which the biomass of the bacteria increases, is basically proportional to the amount of the biomass. So this is basically the differential equation. So what it means is, if you have a certain amount of bacteria, say m of t, the biomass of the bacteria is m of t, then the rate at which the mass gets increased is basically proportional to the amount of the biomass, and this is basically is a differential equation of the exponential growth. So that's what it says. So basically, if you have a bacteria of mass m of t, and if you have a suitable favoring conditions, then it grows exponentially. So that's what it means physically. So this equation basically represents a differential equation for exponential growth, and remember that k has to be greater than 0. If k is less than 0, then it becomes an exponential decay. Fact is that differential equations are extremely useful, and they are used from time to time in modeling of physical phenomena. So why do you use maths? First of all, maths is basically used in order to model something which is physical. So basically, to model a physical phenomena, you use maths, and differential equations are basically used in modeling, and that can be understood from from if you look at various subjects, whether it might be mechanical, electrical, or CS, or whatever, all the physical laws and the relationship between quantities are all expressed in differential equation form. So that has been from the time since maths has started. Okay. Now, after defining what is differential equation and seeing, I mean, why do we need to study differential equation? Let's see what are the different types of differential equations. So let's study the classification of differential equation. So now there are various ways in which differential equations are classified. So first way is based on the variables with respect to which the derivatives appear in the equation. So basically based on the number of independent variables. So based on the variables with respect to which derivatives appear in the equation. So from now on I'll write differential equation as dE just to avoid writing struggle, with respect to which the derivatives appear in the equation. So based on this you have, so what it basically means is number of independent variables in the differential equation. So based on this you have two classification. First is ordinary differential equation, where you have only one independent variable, either x or t most of the time. And then you have the partial differential equation. So ordinary differential equations are called ODEs and partial differential equations are called PDEs. Okay, so ordinary differential equation means the one that involves derivatives with respect to only one variable. So involves derivatives with respect to only one variable. So one independent variable basically. Okay, so example, let me give you a couple of examples. So here you see you have only derivatives with respect to only one variable. So the derivatives is with respect to x. Okay, so that's why this becomes an ordinary differential equation. But sometimes you may have something like this, d square u by square is equal to c square d square u by dx square. So here you have two. So here you have basically derivatives with respect to t and derivatives with respect to x. So in fact this is basically a one-dimensional wave equation. So you can say the partial differential equations are the ones which involves partial derivatives of the unknown function. See, unknown function is what you need to find out when you want to solve. So that's why I'm calling unknown function, or the dependent function or dependent variable y. So here it is u here in the example which I gave you for the PDEs. So it involves partial derivatives of the unknown function with respect to more than one variable. So here you have time and x. Okay, so just to physically explain you, if you have a string, okay, stretched stretch string which is vibrating and stretched, and then if you just give a small disturbance to it, so it just vibrates. Okay, so now u of x comma t basically represents the lateral displacement at any point on the string, lateral displacement at any point on the string at time t. So that's what this equation represents. It basically, once you solve this differential equation, you will get the lateral displacement at any point of the string on a stretched string. Remember, that's important, on a stretched string at time t. So this is typically this is typically called as a one-dimensional wave equation, because it basically once you solve it, it gives the solution for the wave that is set up on a stretched string when it is given a small disturbance. So this is one fundamental classification: ordinary differential equation and partial differential equation. There's another classification based on the order of the differential equation. So let's first see what is an order of the differential equation. So then basically it's a first order differential equation or second order differential equation. So based on that, it is defined first order differential equations or higher order. Higher order means more than one. Higher order is greater than one. So this is one more way of classification. But let's see what is an order. So an order is nothing but an order of the differential equation. So an order of the differential equation is basically the order of the highest order derivative term present in the equation. So for example, let's take this wave equation example. So in this, the highest order derivative term is 2, right? Either you take this term or this term, it's the order is 2. Okay, so this is called the second order PDE because it's a partial differential equation. Now similarly, let's take another example: d square y by dx square plus x cube y over sin x. Now the only derivative term that is involved here is d square y by dx square, and its order is 2 here. It's 2. So therefore this is ordinary differential equation with order 2. Okay, so likewise you have to actually see the highest order term. So let's take another example: d cube y by dx cube plus 4x dy by dx whole square is equal to y d square y by dx square plus ey. Now so here you have the third order derivative term, the first order derivative term, and the second order derivative term. So we have to see the highest order derivative term, and the order of that becomes the order of the differential equation. So here it's the highest order derivative term is d cube by dx cube, and the order of this is 3, and hence it becomes the order of the differential equation. So the order of this differential equation is 3. Okay, now there is another terminology that is used, which is degree of the differential equation. Well, the degree is nothing but the power of the highest order term. So once you have found out the order, then the power of the highest order term, highest order derivative term present in differential equation. So this is after the equation is expressed in polynomial form. Okay, so after you express the equation in polynomial form, so here let's take this very example. So let me explain in polynomial form. So this is the third order term. Now let's put the second order term first, and then the first order term, and then the other terms. Okay, so this is how you express in polynomial form. Now the power of this is basically 1, right? So the power of the highest order term is 1 here, and hence that is the degree of the differential equation. So we have seen how to find out order and how to find out degree of the differential equation. So another classification that describes, so another classification, so we have seen two classifications. One is based on the number of independent variables, or the number of variables to which the derivatives uh, are on the, I mean, the number of variables with respect to which the derivatives exist in the equation. So that was one classification, and based on that we found out that leads to basically ordinary differential equation and partial differential equation. The second classification was based on the order and the degree, basically on the order. And the third classification, which is very important, is based on linear and non-linear. So we'll see based on what, but the classification leads to linear and non-linear differential equation. So what it means is, a linear differential equation is one where the derivatives and the derivatives and the function, remember this is the unknown function of the dependent variables, are not multiplied together and have degree 1. So basically what it means is, the derivatives of the dependent variable have degree 1, and basically the dependent variable and its derivatives are not multiplied together. That's what it means. So otherwise it is non-linear. Okay, so if you have the product of the dependent variable and its derivatives, then it becomes non-linear. And even if you don't have the multiple of dependent variable and products, but even if the degree is more than 1, so say something like dy by dx whole square terms you have, okay, or you have something like y square into dy by dx, or y into dy by dx, so those kind of terms will make the differential equation non-linear. So by this time you can say that uh, nth order the nth order linear ODE basically exists in this form. So you have the functions of x you may have as the coefficients, and this is the nth order derivative term of y of x plus, so this is again the functions of x can be multiplied together, and this is the n minus 1th derivative of y of x. So similarly like that, so this is a general form of your linear ODE, or linear differential equation, ordinary differential equation. The last term being a naught x y of x is equal to f of x. So here you can see all the derivatives are basically of degree 1. The exponent is the power, they have all 1, and they are not multiplied together. They might be multiplied with the function of x, but they are not, the derivatives of y of x and the y of x are not multiplied, and they don't, I mean, they exist independently. The derivatives don't have product with either lower derivatives or higher derivatives, or they don't have the product with y of x. So this is how a general nth order linear ODE looks like. Another way of like, given an ODE, you have to find out whether it's linear or non-linear. The other way of looking is, multiply the y of x term with c of x. Okay, keep y of x as c of x, and now if you are able to remove c common throughout, then that becomes a linear equation. So this we'll see when we check whether a given equation is linear or non-linear. So basically if you have products, then c you cannot, the constant c you cannot remove common throughout. So one way to check whether an ODE is a linear or non-linear is basically expressed in this form. Otherwise, just keep y of x as c into y of x, and if you are able to remove c common throughout, then it's a linear ODE. So we'll see one example which will describe. So let's take an example: d square y by dx square plus x cube y is equal to sin x. So now in the place of y, if I keep cy, then what will I, so c is some constant, right, into cy plus x cube into cy is equal to sine of x. Now so this becomes basically d square y by dx square, and this becomes c into x cube y is equal to sine x. So now c I can get throughout common, right? So this is possible only when c is common throughout without any exponents on the power or without any power of c. So c I am able to remove common throughout. So this is an example of a linear ODE. So a simple way to check, or you have to just express in that form, in whatever form I described. So the other way of doing is just express the highest derivatives first. So this was 1, then you don't have the, so the coefficient is 0 for the dy by dx term, and for the y term you have the coefficient x cube and then sin x. So these are, so here the coefficient is 1, here the coefficient is 0, here the coefficient is x cube, and the individual derivatives exist without any product, and this is f of x. So this is another way of checking it. So, and remember the order is 1 here, order is 2 here because the order of the highest derivative term, and the degree is 1. So this is, the order is 2 and the degree is 1. So this is, so you can say this is a second order linear ODE. This is a complete way of describing a differential equation. Now another classification is that a linear ODE can be homogeneous or non-homogeneous. Now how do you say homogeneous or non-homogeneous? So homogeneous means, if you look at the general form of the nth order differential equation which I just mentioned, if f of x is 0, or basically the right hand side after expressing in this form. So let me just quickly explain. An yn the derivative plus an minus 1 nth minus 1 derivative, so on. You have a1 y1 y dash the first derivative plus a naught y of x is equal to this f of x. Now if this f of x which is 0, then you say the linear ODE is homogeneous, otherwise it is a non-homogeneous. So now this example which we took here, you had the f of x as sine of x, so this was a non-homogeneous case. Okay, so this was basically a non-homogeneous linear ODE case. So this is just a small classification among linear ODEs. Okay, so let me just describe one example. So another example is 1 plus x square d square y by dx square the third derivative, and then you have the sin x into d square y by dx square minus 4 into dy by dx plus y is equal to 0. So this is just expressed in the standard form of, where you have, these are the third order derivative, the second order derivative, the first order derivative, and the function y. But this f of x is 0. Okay, and here you can see the derivatives are not multiplied together and they are not multiplied with y also, and all have degree 1. So this is a perfect example of a linear ODE, because each of the derivatives and the unknown function, each of the derivatives of the unknown function and the unknown function itself has degree 1 and they are not multiplied together. So these are the two conditions. Or you can always check with this, if you put y is equal to cy, you can take out c common. Okay, and all the coefficients are either constants or functions of x. Okay, And now this is a homogeneous case. This is a homogeneous case because f of x is 0 or the right hand time is 0. Okay, so just to describe this, this is a linear ODE, a homogeneous linear ODE, linear homogeneous, let me just describe in this way: linear homogeneous differential equation with order as 3 here and degree as 1. So degree is 1 here, you can see the degree is 1 here. So this is a complete way of describing. First is whether it's a ODE or PDE, so that's why ODE. And the second other classification is order and degree, so that we have seen. And the third classification is whether it's linear or non-linear, and a sub classification of linear is homogeneous or non-homogeneous. So this is all about describing a, so this section was all about what is a differential equation, why we need to study differential equation, and how do we classify differential equations. There are three ways of classifying which we have seen. Okay, so now let's see how to form a differential equation. So let's see how to form a differential equation. Well, this is rarely seen because generally a differential equation will be given and your objective always will be to solve and find out the unknown function y of x. Okay, but forming a differential equation also something which you should know, because say suppose I give you y square is equal to x, or y, for example, y is equal to x square plus some constant. So basically you have to differentiate as many times as there are number of arbitrary constants. So that is how you form it. Differentiate as many times as there are arbitrary constants. Okay, so basically in this case you will know that will be will be the number of arbitrary constants. So number I am just writing as no and dot, so order becomes basically the number of arbitrary constants. So just to explain this, just take a general straight line where a and b are constants, a and b are arbitrary constants. So now if I differentiate once, I will get dy by dx is equal to ax, and is equal to a, sorry, b will be a constant, so basically a into dx by dx plus 0. So this will be dy by dx is equal to a into 1, which is a. Okay, so this is differentiating once. Now differentiating second time, you will get d square by dx square, because still we are left with one arbitrary constants a and b can take anything. So now it will be 0. So this is basically a differential equation of this general family of straight lines where a and b are constants. So what it means is the order is 2 here, and that was the number of arbitrary constants. Remember, a and b are the arbitrary constants. Two. Okay, so this is a general thing. So order is the number of arbitrary constants. Or if you look back in a reverse way, you can say that if you want to solve this, okay, and find out the complete solution. Complete solution means, what I mean is that if I d square by dx is equal to 0, if I just integrate it twice, I'll be ending up getting this equation. But in order to get the complete solution, I need to know, to find complete solution, I need to provide two boundary conditions, or two conditions for a and b. So basically that's the thing. So the order is becomes Order will tell you how many boundary conditions are required in order to get the complete solutions. Otherwise, this will be just the general family of the curves, which here it is straight lines. So general family of curves that satisfies the given differential equation. But in order to get the required curve or get something which is desired, you need to substitute the boundary condition for, and boundary conditions will be basically the number of unknowns and or the number of arbitrary constants. So number of boundary conditions required to get the arbitrary constants. Okay, so looking at the differential equation, you can basically tell that how many arbitrary constants are going to be there when you integrate it, and how many boundary conditions you require. So all that based on the order, and this can be understood when you just start from a curve and then you differentiate it as many times as there are arbitrary constants, and basically then you get the order. So it's all connected. Order is basically connected to the number of arbitrary constants, and that is nothing but the number of boundary conditions that are required in order to get the unknown, the complete form of the unknown. Form is there, but the complete solution or the complete unknown function. Okay, so just to I'll write down some of the differential equations, and just let's list out based on the classification what type of differential equation is. So first is dy by dx is equal to 5 pi. So this is basically an order 1 equation, and it's linear because the derivatives and the terms are multiplied together and the degree is 1. So linear, homogeneous, because this I can express in dy by dx minus 5y is equal to 0. So this f of x term is 0. So this is linear, homogeneous ODE with order 1. Okay, now let me write down another case, which is x square y double dash plus e power x y dash is equal to 1 by y. Okay, so this was all about differential equations. So I've just listed out some of the equations here, and I have found out, say for example, dy by dx is 5 pi, and so this is, if we express in the form which we have discussed, it becomes a linear homogeneous ODE with order 1. Now the second example which I have just written it, when I just take y to the left hand side, it becomes something like this. Now you can say that each term on the left hand side is basically a derivative of the unknown function and the derivative. So y is the unknown function and y double dash is the second order derivative. So each derivative on the second order derivative and the y are multiplied here, and in the second term also you have y and y dash together. So it is a non-linear equation. It's a ODE because you don't have the partial derivative terms. The order is basically which order derivative term is the highest. So there is only the second order derivative terms are present, the third order is not present. So second order, so that becomes the order of the differential equation, and the degree is the power of this order second term, which is 1. Okay, so this basically represents all the ideas which we have discussed. Okay, so now let's do some solving exercises, solving differential equations, various types of differential equations.